Hello everyone, hope you're well. We're looking at fluid systems over the next few lessons. That will cover this lesson and the next lesson, which will be looking at dams, holding huge amounts of water back. We need to look at fluid flow through a pipe. So imagine a hose pipe, and you put your finger on the end of it and the water comes out quicker. We need to understand a little bit of maths behind that. And then we're going to be looking at the other one is Archimedes' principle. So why do things float? I mean, you do it in year 9, I think, but a little bit more depth than that. So this is about pressure. The last couple of lessons I've asked you to have a read about pressure. And if you ever ask for a definition of pressure, which probably wouldn't be on this, try and think about what causes it. So if you push a pin into a wall or stand on something, that causes pressure. But that's we're thinking about solids, which is a decent, a logical way to go. So here we have something pushing into the blue wall. The bigger the force, the bigger pressure. You push harder, the bigger pressure on the wall. But people mix up pressure and force. They use it as the same thing, which it isn't. And then you can see there's a proportionality, therefore, between force and pressure, but there's an inverse proportionality between pressure and area. So if you decrease the area, you increase the pressure. So if you make the brown thing thinner, like a pin, so the area becomes smaller, the pressure becomes bigger. So that's how we deal with it with a solid. In a fluid, it covers liquids and gases. It's called a fluid because these particles can flow. They can move around. They're not always next to the same particle. The red ones at that moment in time that are causing the pressure. So pressure is caused by the particles bouncing on the edges of a container, changing direction and exerting a force as they do that. Newton's third law says every action has an equal and opposite reaction. So if A pushes B, B pushes A. So you know that the particles get changed, have their direction changed. So the wall must push against the particle. So therefore the particle pushes against the wall. And that's the cause of pressure. How could you increase pressure? Well, you could put more particles in. You could heat them up so they go quicker, so they bang against the sides much more strongly. You could get heavier particles. So that's all the theory behind pressure. So this is what we're dealing with. This is why it's in this topic. Dams are amazing, easy to drive, just take for granted. Huge amount of died making the dam, which is the most famous dam, not the biggest. Start of GoldenEye. Look at that. It's a James Bond film. He does a crazy thing on a dam. But the amount of water you can see that's being held, the force and the pressure on that wall is unbelievable. So we need to be able to understand that. Here's an example of where pressure becomes bigger. So you would probably know that if you go deeper down, things can break. A submarine has a maximum depth that it can go to without starting to crack and implode, I suppose. If you swim just a few meters down, your ears will pop and you'll need to kind of pop them yourself. So hopefully that as we increase our depth, the pressure increases. So pressure therefore is proportional to depth. Now there's not a lot else to it really, because this is the formula for pressure in a fluid. H stands for depth. Now I know H stands for height, and that's probably the main thing you'll need to try and remember from this presentation, that H means depth, not height. G is your gravitational constant, 9.81, and rho is your density. That will be the density of the fluid. So that'll be 1,000 for water. That's pure water. If you've got water in like seawater, then it might be 1,020, 1,040. It's got impurities in, so look out for that. So it'll be a little bit more dense. So that's an important formula. Pressure equals rho GH, density times gravitational field strength times height or depth. Yes, it's in the GCSE curriculum. It is in this, but it's kind of hidden inside another formula, which I'll show you now. I'm going to skip that, but just to mention that this retaining wall, if it was made like this, it would struggle a little bit, because as the depth increases, the force will increase, as will the pressure. So the pressure here is much greater than the pressure here. So what do we do? I mean, if you're asked for the pressure or the force, do we give it here or do we give it there? Well, actually, we choose to give an average, which is half down. So that makes remembering what H stands for even more complicated. Not only do you remember its depth from the top, but also remember you just use the depth from the top to halfway point. Otherwise, what you'd be giving is the maximum pressure. So it will all become clear when I show you the exam question. Now, being asked for pressure is a totally different question than being asked for force, because pressure and force are related with this formula. So, as pressure equals force divided by area, if I was to multiply both sides by area, that would say pressure times area equals force. So if you're asked for the force, you would take the pressure, rho hg, and multiply it by the area, A. So that's why the formula for pressure and force look very similar, but if you multiply both sides by A, you will get force. Pressure becomes force because it's multiplied by A, and on this side, multiplied by A, you just get rho hag. So that is the formula for force. Now, force has another name, thrust. We use thrust in year 7. The force on a car. You've come across thrust, hopefully, but yeah, you get used to force meaning thrust in this. So hydrostatic thrust is the name they use. Hydro is a word for water. Static means not moving. So you've got a big amount of water not moving. It's the force that causes. Okay, I'm going to come back to that in the next lesson. So here's the first of 2 exam questions I'm going to show you now. Calculate the area of the water against the dam. I've put this first so you get used to calculating the area. Now, the only time this will be tricky is if the water's not filled up all the way. The area it says the dam is 8 meters wide and the water is 6 meters high. So the area would just be 6 times 8, 48. But if water went up 5 meters and then you had 2 more meters of dam, people in the exam will be thinking, right, do I use 5 meters as the height of the water, or do I use 7 meters as the height of the dam? The 2 meters above that water would be irrelevant. No force on that at all. There's no water pushing against it. So we only ever use the height of the water, not the height of the dam. So as the water level goes down, the force would decrease, and the area that you use in that calculation would decrease. So the area of water against the dam would be 6 times 48, as I said. Get the units right, you're multiplying meters by meters, so that's meters squared. And then you ask for the hydrostatic thrust on the dam wall. Right, I paused it there. So I think I was just talking about the area. So if you've got the area, then you go on to part 2, which is calculating the hydrostatic thrust on the dam wall. So you see that. Just remember that hydrostatic just means standing water. So you can ignore that word. And thrust, that needs to trigger the term force for you. So you'd go through your data sheet and you would find this formula for the hydrostatic thrust on a retaining wall. Rho hag. So you would write down F equals rho hag. Now, rho is easy. It's the density which you're given. In this case, it's 1,000, so it's pure water. G is always 9.81 newtons per kilogram or meters per squared. A, well, we've just worked out A, and I talked about the fact that it's the height of the water multiplied by the width of the water. And then H, well, you've got to remember that H is the depth, but then the most common wrong answers come from using 6 meters. Now, if you use 6 meters as H, it will give you the maximum force, the force here, which is not fair because it's much greater than the force here. You could say here and it'd be fine, but down here the pressure would be very high. Don't swim there, though. you'd get sucked through the turbine, which wouldn't be nice. So your depth, we have to take the average depth to give an average force, which is a more useful figure for us to use. So you have to try and remember that h is half of the full depth. So in this case, we would use 3 meters as h. It's always the case. You're always going to look for the depth. How deep does the water go, or how high is the water? Half that number, and that gives you your value for h. So this answer would be F equals rho GAH, which would be 1000 times 9.81 times A, which is 48, multiplied by H, which is 3. And that will give you the hydrostatic thrust. And then you think about your units, and thrust, as we've said, is a force. So like any force, the units are newtons. Okay, so to show me that you've listened, I would like you just to send me the answers to 9 part 1 and 9 part 2, and also the answers to this question. So this doesn't have a separate section where you work out the area. This is just straight for asking for the hydrostatic thrust on the dam. So I won't say anything about this one. You can pause the video, jot the values down, and all I want is a hydrostatic thrust for this question. And that's it for today. Okay, so send me the answers to those two on an email if you would. Take care, and I'll send another video hopefully to finish up this topic next lesson. Thank you.